Okay, so let me briefly remind you where we are. So this is, by the way, kind of the outline of what was happening during this conference, and you can see most of the time it's eaten up by GLC2, which is kind of only makes sense because it's like a lifetime 50-page paper. So, and we ate up most of GLC3 just because it's very technical. So like the discussion yesterday that it's a series is so very over the top. I mean, and I forget whose remark was it was Grubier's question, but whose question was it? Oh, no, was it yeah, your question, but so in classical theory, but the more functions, Isaacson here involved a lot of analysis. And here, this analysis gets transformed also in some kind of technical work. And that work is in mostly TLC3. It was suppressed, compressed. Anyways, so here's where we are. So we have D mode D going to make the left fiber. And so what we said yesterday, here is the mode of GIs. Here, integral lawsuit in check support on the reducible locus. These functors reduce support pair of mutual adjoint functors. And yesterday we indicated the proof that they are mutually inverse equivalencies. And so when I write this, I need all the arrows in all the directions to use. Again, the arrows on the left and arrows on the left go in the direction. And also here, thus, here, heats. Irreducible. So this is L. Thus, this is level joint. And so this is the functor of so J spec was the embedding of the irreducible locus. So here J spec of this called J spec goes up. And so there is a complete analogous diagram where I put temp here and I just don't want to write it to save time. Temp, but in this case, you will replace intco nil by quasi-co. So now, what happened in the previous hour? So we can forgot to say it's the work that preceded the GLC series, the work of Joachim and Sam. So what we proved is that LG temp as if D mod of G temp this conserves. That's the theorem from the last problem. That implies that L to cut. Repeating what Joachim said, D1 from G plus to as a code was to irreducible. So the reason for that is that Cuspidal category viewed as a subcategory instead of LG is contained in the temporal category.
We don't know it is yet. No?
No, that's what we proved. So that's what Joachim proved the previous one. Yeah. So recap, so that we know that these guys are mutually inverse. We want to show that these guys are mutually inverse, but because everything here commutes, it's enough to check these guys are mutually inverse. And what we already know is that it's conservative. So
Hey, can I ask you about, so, I thought the Carolyn in Ryan's lecture was about the doctor from, into you called LSG check being conservative.
Correct.
One goes that it was not something.
So this was conservative.
Yes, I
For instance, the formal consequence of this was conservative. Like namely, if you view this is a subcategory inside 1G, view the subcategory, this guy is contained here. And then all the diagrams to be Jewish. We go. This is the community that.
Sure, as a consequence of the above.
As yes.
So, yeah, in other words, there's a deep theorem that is confusing here, which we'll explain yesterday, which says that this functor, LD functor from cusp the theory is false. But only cusp all have the theory is false. Well, it's
Not the polls in fact of the composition. Let's really so there will be question time. I think we have the assertion that y LG counter sounds plus reduced. So there's something to be said here. I didn't actually quite say this in the talk. Let's respond to the question time passing this on. So once you know this, everything on earth commutes, therefore this consideration is like this. So goal for the rest of today is to show that LG plus L is fully uniform. And so we'll approach it from a particular point of view.
Sorry, yes. L plus, LG plus is just a restriction of
Yes.
LG, right? So
Yes.
it's equivalent, it's
It's-
identity.
Yes, it's a restriction, but also the quote. Everything commutes. Correct. So let me just for a second consider the template version of this functors. So let's consider LG L temp composed with LG temp. So this is an endofunctor now of quasi-co, and we're looking at the template category. And by construction, all these functors are linear with respect to the action of itself. Therefore, this endofunctor is given by tensoring with an object, and moreover, because it's a monad, it's a position of functor with its right adjoint, it's moreover it's an algebra. So the functor is given by tensoring with an object. Or AG is associative algebra inside of and similarly, this composition LG cusp L.
An exercise for everyone is that AG is the following things. You take this vacuum punctor A sheet, take its internal endomorphism to the action of this T check on D of G.
So this will be said, emphasized by Kevin with the stop. So the nature of LG, what it actually amounts to will be the essence of Kevin stop. So this is tensoring by, as we call it, AG cusp, where AG cusp is just a restriction of AG to the reducible locus. And so the fully faithfulness amounts to the following assertion. So here, fully faithfulness is the same thing as saying that the unit, namely O of losses, we check, mapping to AG, the unit map is an isomorphism. And the fully faithfulness on the cuspidal part, which we know is logically equivalent to this, is equivalent to the same thing as that fully faithfulness. Is equivalent to on the irreducible locus to this AG cusp being an isomorphism. And let me say that the fact that we know that our Langlands after is an equivalent to the Eisenstein part is the following assertion. So know already that if you take this unit and if you take the set theoretic upper shriek of it to the reducible locus, let me call it iota. So iota is the embedding of the reducible locus, but I kind of at, meaning the set theoretic, like with supports. So if you take this O of cis, so iota spec, this hat indicates formal completion. The AG is an iso. So like we're interested in this more because we know that when you set the rate to reducible locus, restrict the reducible locus, it becomes an isomorphism, but something bad may still happen on the irreducible locus, so that's our focus today. So yeah, emphasize we won't throw these guys in isomorphism.
Maybe you mean MG cusp length of joint.
Pardon me?
You mean the MG cusp length of joint.
Fully faithful, yes.
The plural MG cusp.
Where?
Oh, yeah. There is no one see.
Yes. All right. So now I'll say the key theorem that
Is J spec is the inclusion.
J spec is the inclusion of the irreducible locus, and iota spec is the inclusion of the reducible locus.
Oh, I see.
Yeah. Sorry.
Okay. All right. So now I'll say something drastic, which will be kind of the theorem that will occupy this talk and talk by Lynn. So it's called ambidexterity. It's not surprising to believe in license. Ambidexterity. And it says the following: that the convert LG plus is ambidextrous. Who knows the word? Raise your hand. Right. And what this means is that, in other words, ambidextrous means that its left adjoint is isomorphic to its right adjoint. So we already know that the left adjoint exists. We claim that right adjoint also exists. It actually happens to be isomorphic to the left adjoint. It's kind of. So let me give an example of something ambidextrous. In ordinary mathematics, if you have a function from vector spaces to vector spaces, given by tensoring with a finite dimensional vector space, this is ambidextrous. This left adjoint is given by tensoring with a dual, and the right adjoint is tensoring by the dual. So that's the kind of thing that's ambidextrous. And they're not so many, I don't know, arguably, not so many ambidextrous things in nature. Like, of course, an equivalence of categories ambidextrous. This guy is supposed to be an equivalence of categories, so that's why we expect it to be ambidextrous, but it turned out we can prove it like a priori, and that's what leads to the proof. But so let me right away deduce a consequence. The corollary is AG cusp is perfect as an object of quasi-code. A compact. So when is an object compact? When perfect, the functor of tensoring by it preserves compactness. But I claim the functor of tensoring by it, preserves compactness by virtue perfect and self-dual. Let's see what the functor of tensoring by it is. So functor of tensoring by it is what they said, this composition LG plus L. So, and I claim that this functor not only does it preserve compactness, it's right adjoint is itself. Namely, take the right adjoint of this guy plus take the right adjoint. How do we calculate the right adjoint? We write the joints in the opposite order. So it's LG plus LR, LG plus R. But this is the same as LG plus. And here we use ambidexterity, saying that LGR is the same as LGL. So you see that the right adjoint of this functor is itself. The particular functor admits the right adjoint, so it implies that the object is perfect, and this right adjoint is itself. So this right adjoint would have been the dual of this guy, but the functor is itself, so the dual is isomorphic to itself.
That's basically cut off.
Pardon me?
Basically cut off.
AG.
Your AG tensor.
Cusp. Yeah. All right. And no. So we always talk here. We talk about AG cusp. We are on the cusp.
There's a restriction there, but we only know ambidexterity. When we talk about ambidexterity over the current over the
AG cusp is the restriction of AG to the irreducible part. What? Yes, AG and AG cusp was also defined, and it's the restriction. Yeah. Yeah. Okay. But the ambidexterity is only about the cuspidal. We don't know this ambidexterity for all of AG. Okay.
Yeah,
all right.
You typically bypass where an argument is going to be like you really need to be restricting to customer focus.
In the proof.
Yeah.
Yeah. There would be two parts. One is that with domination by Gaitsgory, that it happens over quasi-compact local subsets. Maybe you could get around a bit, but the main part is that when we think about opers mapping to local systems, this map will be in some sense proper specifically over the irreducible locus. That's where like irreducibility will force some properness, and that's where everything happens.
And so in the same style, between you and ambidexterity, like how sad should we be about only knowing ambidexterity?
Sad. We should
like suppose you knew that it everything. Would it prove it's an immediate clear?
No, we will still need a certain computation that so like Kevin's clock will be twice as short if we knew it on the whole thing, right, Sam?
I think that if you knew a priori that this AG was perfect, you'd be in really good shape.
We could wiggle ourselves out faster, but at least Kevin's clock will be twice as short. We'll kind of Kevin's clock will say that to prove this isomorphism that we need here, we could
and
using this.
If you knew that, if you know this and you know that it's perfect everywhere.
So the argument will be easier. Okay. All right. Okay, so now I'm launching the proof of this ambidexterity, and there will be two parts. So I'll do part one, and Lynn will do part two. Okay, So now comes the topic that we should have discussed maybe from the beginning. It's a general topic about duality of digit categories. But we mentioned it kind of in passing many times, but it never said what it is. So if you have a digit category, you always think about compactly generated categories. So it's dual. You can think of it as a functor with a category of continuous functors from C to vector spaces. Or you can explicitly describe it as follows. So your category being compactly generated, it's the incompletion of its compact objects, and this C dual is the incompletion of the opposite category. It's really the opposite. So here are the rules of the game. So, and well, but this duality is really duality in PRL. So you consider the symmetric monoidal category of these categories. It has Lewis tensor product, and dual is the dual object. So in other words, if you have C and C check, there is the evaluation function to that, which is obvious from this picture. Just on compact objects, we just pair. And there is also the unit. Unit, you can think of it as an object in C tensor C check. So mapping that to C tensor C check. And as usual, so they have to satisfy it as unit axioms, and the knowledge of either of these determines. If you give yourself the unit as an object C tensor D, then there will be at most one way in which D is the dual of C. Okay, this is one thing. Also, that if you have a functor from C to D, as an arbitrary symmetric monoidal category, you will have a dual functor, so C check from D check to D check to C check, but now there is something special that happens, something specific to categories that I want to emphasize. We can use principally this part and with Winstar. So suppose you have a functor, so suppose you found the C from F from C to D, F preserves covariance. And so in this case, it remains right adjoint. But also you can do something else. So because it preserves compactness, so you can consider the functor, we call it, we know that the same letter F, but you can take the opposite of F and consider the functor from C off. DC off. Let me call this functor F off. And now you can extend this functor, and we said the extension of that is the Google category. So we obtain from here, extending the functor from C check, D check, we should still know that the same character F off. And so here comes the lemma, which would be used multiple times. F off. No, goes from C check to D check, and this dual functor goes from D check to C check. So it's and F check are only joined there. Yeah.
So F off is F hard.
Pardon?
F off is F hard.
In other words, F off is F object, equivalent statement. So let me just say in the notational words for this F off. So the way we'll think of it as follows. So because I said that, so let me denote by abstract reality, and that's the way I like to think of it, is this contravariant functor from a C compact object to C check compact object. Again, C check compact objects are really the opposite category. This is the tautological functor of an object's really identity from the category that's so it's dual. So you should think of like f of on compact objects as apply this tautological radiality, apply f now ed. Like this formula just expresses what f of is in compact object. In this formula, that's enough. You know, abstract. That's nothing in this abstract framework. All right. Okay, look. What did I forget? So, so example that we use the whole time. If I suppose C is the category of D modules from some quasi-compact variable. Here, by its quasi-compact variable. So in this case, the category, well, it's compactly generated, but it's actually self-dual. So in this case, you check this isomorphic to C, and I will tell you what this reality data is. Here's what the evaluation map is.
Which is at first, I said that for people who haven't seen this lemma thing before, I don't know that it's extremely asymmetric between F and R for a good reason. That it only makes sense to restrict F to compact objects, not FR.
Absolutely, because FR does not preserve vacuums.
And in one possible way, you could try to reconstruct this lemma.
So I want to define the algorithm, I want to define this evaluation functor. What is it? It's comparing. And we've seen it also yesterday. So you denote it this way, and what it does is to let take a pair of objects, you tensor them up in the D module way, the sheet way. In other words, sheet restrict to the diagonal, and you take the rank chains on one. So, properly speaking, it should be slightly renormalized because it's wide stacked. We're forgetting about such nonsense. So if y is a variety, that's literally this. So this is your evaluation, and here's your unit. Unit is you take delta lower star of the dualizing sheet of y as delta is the diagonal. The D module y times y, but God's inversible. This category is in sense a product, so D mod y with itself. D modules of the product are the D modules one factor into the other. So this is the unit of it. Now let me tell you about weight. But this implies that there's some weird identification between compact objects D modules from y with its opposite. Yeah, so there's a contravariant automorphism of the static compact objects. What if yeah, well, it is the reality. So this kind of tautological, we think that the road over there, when you see check happens to something complete, it becomes a very complete functor. And in this case, this is very reality.
Okay, everybody knows.
Pardon me?
I think everybody knows that it's just.
Yeah. No, everybody knows it. So let's see. So if everybody knows it, let's see. Suppose you have a functor from y1 map from y1 to y2. There is a map, yeah. So we can consider f lower star functor from d mod y1 to d mod y2. So now using this identification, we can think of this as a functor from d mod by 2 to d mod by 1. What functor is that? So the claim is that this functor is actually f of the tree.
Also,
Yeah. But let's. Who knows what that is? Well, there was a condition that, like, for this to make sense, the functor had to preserve compactness, and for this f has to be proper. So I would write it's f lower sheet, but it's actually the same as f lower star because the map is proper. And f lower sheet is really not defined for not proper maps. But so f is proper. Now suppose f is smooth. So in this case, f of the sheet preserves compactness, and I can ask what is f of the sheet of? Who knows? Okay, you said everybody knows that.
okay, so
So this actually f is upper star in the model setting. It's the left adjoint to f lower star, and it exists for smooth models. These are the rules of the game. Anyway, we're not getting on. So why we talk about reality? So let's take U to be a quasi-compact open inside 1G. And so we obtain that D mod on U is self-dual. And so we're being very careful here not to take Bungie all of Bungie, because Bungie is not quasi-compact in the category. Generally, it's really not self-dual. Dual in category model is something else. It so happens by miracle, in fact, the functor that's called the miraculous functor, that it's actually self-dual in a very non-trivial way. We are not discussing it in the school because it's something complicated. So you really should think of the dual of the models of Bungie as different entities. But on the quasi-compact, it's okay. So what I want to do now, I want to show that the subcategory of hospital of the modules is self-dual, and I'll take U to be this open subset that appeared in just in stock. It's large enough open such that every hospital is star extension from there. So what you say is to take U to be large enough.
There may have been a question.
Yeah, I'm just finishing enough so that J, so that if F is in D mod G, so then F being over star F star F is an SMO, so that's what Justin said. There exists U such.
Does the non-trivial self-duality of D mod 1G under the Lagrange functor correspond to an easier one?
It is a third reality.
Okay.
So that's why it was expected, but it's geometrically, it's a very non-trivial procedure. It's really called miraculous function defined by Drinfeld. And it does something weird. From compact objects to compact objects. Exactly. So I'm saying that duality is a contravariant self-equivalence of compact objects, or the category of compact D modules.
But it's not from C compact O.
It is, yeah.
But C is not.
So contravariant functor
It's contravariant.
is contravariant. Yes, it's very duality.
This is from C compact. The target is not the same. Source is not.
Yeah, you didn't write up and you wanted about. More open.
We will write FO.
Yeah. No, that's from CC to C check CI.
Sort of cool. It's good. What's the reason? It's good. Easily.
Let's not, let me not, I'll get confused, I think it's all good as written.
Yeah.
It's okay, it's like empty discussion, it's all okay is written.
No, it's not okay, and it's confusing people.
Okay.
So AC is impossible. Effect is also impossible. That's some equivalence between coherent impossible and coherent impossible. Also. Where is the up? Here. So there's CC, which is coherent modules, and then there's C check C, which is also coherent modules. Right? Fact is supposed to be equivalent to CC and up.
This category, the category, the fact of this object is equivalent to itself. Yeah, that's what I'm saying. The category equivalent to itself, that means of the contravariant of the whole. Just look at this one.
Look at what you wrote. You wrote functor from CC.
Okay, discussion suppressed, and two question time. I mean,
So that's a contravariant function.
yeah,
Then ID.
yes, just the only, okay, just the only non-trivial content is this non-trivial contravariant self-duality on cosine modulus, which is residuality. That's the only non-trivial content here. All right, so suppose I have a category. So we're talking about the compactly generated world, and in the full subcategory here, so it will be C1. So with a pair of adjoint functors like this, like so. I'll call it E and EL. So, pardon?
We shouldn't go to the left.
So as we mentioned before, so this pair will automatically induce E dual, and it will be EL dual with general graph. So now, I'll take C to be D modules. Yeah, so we just go back to here. So here I have D modules on U embedded by means of J lower star into D modules on bun G. And so here I have D modules on bun G plus. And so we know that this embedding that we call E, so due to this formula, factors through this. So let me call this EU. So this composite functor is by definition fully faithful. This is fully faithful. So this is also fully faithful. And I want to apply this paradigm to here. So I'm talking about a pair of categories. So a category is full subcategory. So D modules on U and the cuspidal subcategory U is a full subcategory there. So I can take D module. So I pass to the dual, and I know that dual of this is itself. And because of this, I obtain the dual of the cuspidal subcategory. So it will be EU dual and will be EUL. EUL dual, we obtain that this is also a subcategory here. So lemma, it's the same one. So D mod Bungee cusp dual equals D mod Bungee cusp as subcategories in D mod U. So here there is a statement with content. So again, I emphasize that. So you have a full subcategory, you obtain a full subcategory in the dual, but the dual of C is identified with itself by this Verdier duality. And I can ask, what is the corresponding subcategory in the dual? And I'm saying it's the same guy. So there's something to prove here, and let me say what there is to prove. So D mod Bungee cusp viewed as a subcategory inside D mod U can be realized. So it's proof of the lemma. Can be realized as follows, as the right perp of the following collection of objects. As the right perp of the following. You take this Schmidt-Eisenstein series and you star restrict them from all of Bungee to U. So if you unwind the definition, you will see that Bungee cusp is exactly that. So, but D mod Bungee cusp dual also viewed as subcategory in D mod U due to Verdier duality will be realized as follows. Is can be realized if you unwind these definitions exactly with Verdier duality as the perp of the following guys. You take Verdier duality on U and so let me say Verdier duality on the step that you started from. Some binary. So there effectively you also start with quasi-compact open. So, and it seems like we have two different collections of objects. So here it's these guys, and here these guys conjugated by Verdier duality. And you want to show that the perp condition is the same. So this is the content of this assertion, and let's prove it.
We mean apply to compact objects.
Pardon me? Apply to compact objects on this banana. Sorry?
It was not this inclusion of demon Bungee cusp into demon U, because
Say again?
why is the inclusion of demon Bungee cusp into demon U? So this is an egg, but
So I'm saying if you have a custom guy, it's automatically star extended from that view.
oh, so there is one U for which
That's what I said. It's like, remember,
yeah.
from Justin's stop. He said it's you that with this property. And so in other words, this inclusion, E factors to this. So that's exactly what the formula says. I'd call it EU.
Third, why does EU have in left rotor?
Pardon me?
Why does EU have the left rotor?
As a
Left rotor,
left, I don't know the word, last word.
left rotor.
The left adjoint.
Left adjoint. Exercise from here. So in fact, you can see that if you take the left adjoint for all of bungee here, we claim that this left adjoint factors through the restriction for bungee to D mod U. In other words, I claim that if you apply the left adjoint to all of E, if you apply it to a guy that's supported of U, you will get 0. And it's immediate from this point. Good question.
So you said got M down.
Yeah. I'm going from, it's Eisen series goes from Banem. Effectively, because you're restricting to quasi-compact open of bungee, you only care about the restriction of your guy to a quasi-compact open of Banem. Okay. So what are we talking about here? So let's look at what this functor is. This functor is covariant. Do Verdier duality to a compact object, you do some covariant functor, you do Verdier duality. Again, it's a covariant functor. And so I want to say it's I's star. Yeah, star. So what's I's star? So Justin defines for us Eisenstein series, they were given by this diagram. So you have this one P going to one M and more to the Q, and to one E and more to the whole E, and IC was Q upper star Q lower field. So the existence of this has to be justified, but doesn't justify that. And I star is the Verdier conjugate. So that's why I wrote all these formulas. So it will be Q upper sheet, but because the work is smooth, Q upper sheet is the same as Q upper star, which at some logical shift times E star. And this work is really not proper. So these H3 as I star are really different. And what I'm saying here, they're really, really different. And H3 really stands compact objects and banana compact objects, bungee. Look at this functor, it stands compact objects, banana, something which is not compact bungee. Functors are different. However, I'm not dealing with these functors. I'm taking these both functors and then restricting them to quasi-compact open. And so the claim is that functors I sheet and I star after composing with J log upper star restricted quasi-compacts are finite extensions of one another. In other words, I sheet can be written as a finite extension of copies of I star and vice versa. Like this difference between sheet and star, it plays off at like this form in the fundamental domain. On the quasi-compact open, they are kind of on equal footing. Are, I don't know, finite extensions of copies of each other. It's a very confusing sentence. Let me say it again. So this guy is a finite extension of copies of this, and this guy is a finite extension of copies of this. Okay. And that's why these conditions are good. Functorial, yeah. So there's canonical for every U, there's functorial illustration from this, whose both are copies of this, and vice versa.
Can you say that this thing's written down?
Are you?
Well, precise version of this thing's written down.
Where?
Yeah.
I think, please remember for question time, okay? Yes.
Wait a second, this claim is saying something like precise and confusing. The thing over there is like you just say some set of objects brought to some set.
It's saying that like whatever is generated by these objects is something that's generated by these objects. That's what I'm saying. I think, yeah.
Also, copies and Boolean translations.
Copying the copies including homological shapes.
So like 0 is finite extension of copies of it.
Don't confuse me.
Yeah, it's a refinement is true that there's an invertible object such that you can write I star as I streak of tensoring to that invertible object. True.
It's not invertible. It's like it's not
Okay.
not invertible.
And what is the finite index?
Pardon me?
What is the index set? What's this finite?
A great question. It's a It's for every given U, it's a finite subset of what we call lambda pos. Lambda is the lambda pos is positive part of the root lattice. Whatever general spanned by positive simple roots. And you take for every U, you take finite subset of that. That's the root subset. And this, it comes from strata of Drinker's compactification. It basically means J low sheet versus the J low stock on Drinker's compactification. That's where it comes from. Right. Read this for time being. Let me see where I am. Oops. All right. So let me remind you what we're doing. So we're considering the lambda functor d mod u plus 2 quasi-cone log 6 g check irreducible. This is our LG cusp. And so the ambidexterity theorem said that it's left adjoint equals its right adjoint. So, but now we'll consider another functor, namely the dual functor. So we'll have LG cusp dual. And that goes, well, the category of quasi-compact sheets in some quasi-compact stack is also subdual, let's say by naive duality, just perfect object goes to its naive dual. And we just proved that this category is also self-dual, just this lamb identified the dual of the cuspidal category with itself by this somewhat non-trivial procedure. And so this theorem, the ambidexterity theorem, will split into two parts. So theorem one is that LG cusp dual is the left adjoint. And this is what I'll prove now. And theorem two, which is proved by separate methods, is that LG cusp dual is the right adjoint. And so this will be done by Lin after lunch. And let me say that this is where this fundamental commutative diagram really plays a crucial role. For the proof of theorem one, we'll use the lower portion, just that. And for the proof of theorem two, we use the partial, the so forth. So that's how they play out against each other. So again, for the rest of this talk, we'll be concerned with identifying these two functors. I want to have a breather for 2 minutes. Let's ask questions, and Sam will answer. Or you can ask questions and answer them.
If that's allowed, can I take 5 minutes?
Please, yes. I want to drink some water. Okay, just you do it.
I just want to explain that you took the shot. I just want to explain a little bit of the geometric intuition that's in Dennis's head right now. So he said something about the fundamental domain, and I just want to briefly draw a picture of it. Of what he's saying. So this is my best attempt to communicate these things to people. So I don't know if it's great, but okay, like that. And we'll go kind of up here. So this is a picture of something like an SL2. And this is the open, which is equal to the semi-stable. Apologies to people who've heard me say this several times. This is the semi-stable bundles. Each one of these, what's happening in this picture is that each of these is going to be some locally closed thing. So this is kind of open, this is some locally closed, this is some locally closed. The union of this plus this plus this is open. That's the structure of the geometry. Each of these are Harder-Narasimhan strata. So these are indexed by integers. So this will be maybe I'll Narcimon 1, connecting Narcimon 2, keep going, and here this part of Narcimon n is equal to all extensions L to E to L check 0, where the degree of L is equal to n, greater than 0. So the same as if you take this stack, aka some part of bund B, then it maps in a locally closed way to bund G, bund SL2, and moreover, this gives you a stratification where the complement of these semi-stable bundles are just the things that aren't in the image. And for n sufficiently large, well, this extension will automatically split. And so we have an exercise to set this harder than everything on n is going to be what's called a unipotent gerb over bun GM n for n sufficiently large. Where the boundary depends on the units. So this was sort of picture, it's getting smaller and smaller, but once you get far away, then it just turns into this bun GMN, at least at the level of sheaves. So first of all, this is sort of part of what Justin was saying about how the non-quasi, just in the very first talk of the week, how the non-quasi compactness of bun G is kind of remarkable and kind of stacky. So if you have something smooth, like the dimensions here are dropping at each stage, you have like open, locally closed, locally closed, locally closed, locally closed, and this is illegal in algebraic geometry, kind of usually, at least if everything's going to be smooth, because the dimensions are supposed to drop at each stage, but the here the dimensions are allowed to be very negative because it stacks, and then sort of an exercise also is that this like constant term n functor is equal to the streak restriction to this Narcimon stratum n for n sufficiently large. Where what that means is that when you're restricting, like, okay, one thing I can do is I could restrict the stratum. I'm saying once n is sufficiently large, the stratum is just like a unipotent gerb, meaning it has the same category of D modules as this object, this bun GMN. We also have this constant term functor that goes from D modules on bun G to D module bun GMN, and so that's sort of the relationship between a lot of the stuff that's going on. This is why custom D modules are automatically extended from when quasi back open. Yeah.
Same.
Yeah.
Right, so a couple of questions about the geometry of this guy.
Sure.
So are there enough line bundles on this guy to cut out these strata via like virtual Cartier divisors?
No, the numbers jump by 2.
Oh,
So
okay.
yeah.
What about with like not virtual Cartier divisors, but like zero sections of some vector bundles? And then the follow-up, if it's a little worse than that, is can you go one stratum with a vector bundle, then look at a vector bundle on that, and then go one more? It's sort of, you can't jump n stages, but you can go one at a time.
Okay, I didn't prepare it. Yeah, locally. Okay.
Guys, ask me more questions.
That was a quick locational question. Was on the n, we mean n component on P, not on the n to make all.
That is correct. So there's the degree and non-bundles. Yeah. Exactly. Sorry. Like from T language out, please. So right. So exactly the same geometry essentially works for any reductive group, but just that then you have to worry about all the parallel. So same picture. And you have to talk about semi-stable bundles for the velocity.
Could you tell me which unipotent gerb, and then maybe for two adjacent numbers, how glue those two strata together?
So the which unipotent gerb, so yeah, so what's really happening here is like okay, so it's the unipotent gerb has So, okay, this harder nourishing on n, again, it's really just kind of like on the n. And mapping it down to on gm n. And now if I have a line bundle here, what's the fiber? And this is sort of for SL2, the fiber is going to be global sections of L squared with a homological shift by 1. And so the unit like the fiber, like once n is sufficiently large, is just the classifying space for H0 of L squared. And again, for n sufficiently large, that's really a lovely vector bundle over bun GM, and it's just the classifying space of that kind of guy. That answer your question?
That answered the first one.
That answered the first one. How do they glue together? Excessive precision for the moment. Yeah. Yeah, it's possible to say, but science knows, but like you can describe the geometry like in kind of reasonably explicit terms, but I'm not going to do it here.
But I mean, just on a simple level, the problem is that if you have a line sub-bundle and it degenerates into a sub-sheet, then it will go into a square X components. So it's not that, so at the very least, you see that there is some non-trivial correspondence going on in GM. So that cannot be a one-line answer to your question.
Yeah. But in a suitable sense, like the geometry kind of looks like embedding like this into this, and then there's sort of a point mod GM side of here, and it's gonna be roughly the closed, and it's roughly the open. Let's go from one stratum to the next. That's a good local model to have for mind, and it has some of the properties that we've been talking about, like that star and streak extensions are defined. Well, the streak extensions are defined on all the modules. You can see it applies in this case.
And as a local model, am I supposed to imagine that like locally in the up-down direction or locally in the side-to-side and up-down direction?
I don't know what you're
in that picture.
In this picture?
Yeah.
Oh, like the individual stratum here, the side-to-side direction, I guess, is just 1BN.
Yeah.
And I was talking about kind of as you compare one stratum to the next. I thought was the question I was trying to avoid answering.
And to make that be a model of the local picture, do I need to like work on a small piece of the higher dimension stratum, or does globally it look?
The statement is basically it's smooth locally.
Oh. One more question to Sam.
Yeah, can you say something about the geometry of the plane?
No. But there are other questions too.
The Conrad.
So if you're very unstable, so like you're big enough, so it's really like always like fun and but can you then describe the glue encounters? And that's a very good question. Like very unstable, so it's different.
How do you move from one to the next or something? Well,
we do, right? It's like this. It's our favorite. It's a negative. It's our favorite one. So it's a great question. It's like it's a little bit more like we don't need. It's very good question, and we don't need this info for this. Okay, but we'll be very glad to answer it maybe in question time. But it goes in a particular direction. It's very cool, but
yeah, that's one interpretation of the question. But yeah, I mean,
well, I mean, there's a question we can answer.
All right,
I'm ready to proceed.
Okay. Wait, there was one more question.
Yeah.
Could you just go you on?
What was that?
Like how far do you have to go to get you? As in you and Dennis.
You guys and Genesis talk. Basically, once you get to exactly the point where this becomes a unipotent germ, then you went far enough.
2G minus 2. N equals, if S equals G equals G minus 1. Okay. So I want to. So actually, I've never drawn this picture in my mind. So this will take a while. I've never, like, it's the first time I have this particular visual image. All right. Okay. So What are we doing? What are we supposed to prove?
Like the dual of LG cusp is the left adjoint. to
Yes.
LG cusp.
Thank you. Right. But if you took the teachings to heart, this assertion is equivalent to the following. What you actually have to show is that LG cusp L is isomorphic to its own R. So this is equivalent to theorem 1. And so that's what we're going to do. All right. Okay, so I'll redraw some parts of this fundamental commutative diagram. Yeah, please.
How about this next time?
Pardon?
Say that phosphorus going to its home, and then what does this do?
Remember, op is functor from the dual category to the dual category, right? It's conjugate. It's conjugate. C is a functor from. Yes, so C is a function from C to D, F was a function from C to D, and F op was a function from C check to D check. Yeah? But we've identified C with C check and D with D check. Hence, it makes sense to say this. F equals F. So it's not F equal. It's self-dual. The functor is self-dual.
I looked at like the state of and the dual thing. So it's like
Yes, no, we didn't say the word fake here, but now it makes sense, right?
yes.
So with the specified cell dualities, the duality on quasi-co is just naive 1, and on cusp it's this one. With respect to these cell dualities, the functor is its own dual. Conjugate, not dual, conjugate. Its own op. All right. So let me redraw this diagram. Okay, all right. So we deal with the lower portion, but I'll turn it upside down. So we have. I want more space. So we have on G cusp. So embedded into D mod on G, and that goes then into the coefficient functor with G one. Here we have our Langlands functor. G. Yeah. And uses this is my E quasi-co losses G check. So this is my G half. Customer slide equivalence. With at the end. And this is again step. Now we will look at the cheat sheet. All right. And I'll erase this. So now I'll take this diagram and I'll pass to the dual functors on with two ends. So maybe I'll also want. So. But I don't want to dualize this, so therefore this is, no, this one, this is J spec your star, this is E. So to modify it, I'll just do this and I'll write go F compose with E, and I'll write this as gamma check and spec check compose with. So I'll take this diagram and I'll pass to the duals. Now I can't do it because, well, I know what the duals are. I didn't write with the previous diagram because I don't know what the dual of demon of the bunch is as a whole thing. We'll dualize this term by term. And we'll also take the left adjoining term by term. So I have B more but G plus. So here, this is what I'm interested in. It's L G plus dual. So quasi-code. So I can. So right now I'm not doing anything. I'm just rewriting. So I'll write. Maybe I want to do it even. So I want to have it. I want them to have a common part. So reposition it even more. So I'll write red. G one. Here I'll write importance down each of the step. Here I write this. So the first P random go F and then that's the show. So here, so the category rep check is self-dual. Also, if you look at the definition of run space, it remains self-dual. And I'll write the formula you can do with them. And then we'll figure out what they are. And next to it, the right is I'll copy the molecular joints. Feasible. Here is the molecular joint responsive. Note, however, that everything inside is acted on by Reg check run, and here the source is free. So to show that the counters agree, it's enough to evaluate them on vector. So that's what I'm going to do. And if you think what this is, instead of coef, I'll use coef back. And instead of this gamma, it will be just counter global sections. under on losses region. Under global sections. Same thing here. So it will be ProF over E. Let's the chart. And here it's gamma loss to check. Equals to J spec. So and in the previous diagram, I should have said both actually. So the previous diagram, these arrows, you can look at them, they were quotients. So to show that the triangles commute, I should have with the red check. With the red check, these arrows are quotients. And to show that these two functors agree, it's enough to show that these triangles commute. That's what I'm writing. So because these arrows dominate, to show that these arrows agree, it's enough to show that triangles commute. That's what I'm saying. And what we're going to see is that, in fact, these triangles are, what am I saying? So when we're going to see that these triangles are identical, we'll see that both these arrows are agree, and this will show that these arrows. That's the answer. Again, so the logic is that to show that these two functors agree, it's enough to show that these two arrows agree. That's what we're going to show now.
State the obvious, you call them arrows, but they're really objects with these categories.
Yes, so because I replaced them by vectors, it needs to be. Okay, so let's compare it with right going arrows. So what are they? So let's decipher. So gamma versus G check composed with J spec like the left adjoint. Well, left adjoints composed in the opposite order. So this is just J upper star. And this is the functor that produces O. It's the functor that corresponds to the object O in Bloch's Uchet. So it sense that this functor produces an object, and that object is O of Bloch's Uchet irreducible. What was it? It was the left. And with the dual, it's exactly the same thing. So A lower star is also again upper star, and the dual of global sections is again. So the naive reality, that's how it works. So this is again J spec upper star O looks in G check. And so this object is again produces just O.
That is a quick question.
Yes.
Are both these right going arrows, are they symmetric monoidal?
No, this is vect. No, that. Why did you ask this question?
Well, that would be one reason that the object would be O.
Sure, it is symmetrical. Now I'm just saying what it is.
Okay.
Again, so I feel slightly bad that I erased rep check prematurely. So again, I wanted to say what I said already 2 times. So I wanted to show these 2 arrows coincide. And for that, it was enough to show that when I started directly check, if I know that these arrows coincide, and if I know that these arrows coincide, then I know that these arrows coincide, because when I started directly check, these counters, they dominate. But to prove the continuity of this diagram, it's enough to start with that, because everything is inside of that one directly check line. So again, everything what I said, because again, it's much better. So far we've identified this with this. And here kind of nothing happened, but something will happen when I try to identify these guys. So let me say what these objects are. And so this is the crux of the proof. This is the place where something really happens. So let's first talk about this. So I'm talking about coefficient embedding E left adjoint. So this left adjoint of E composed with coefficient back. So this is an object, and which object is this? It's EL of what we call the vacuum planetary object. So this is EL. Pardon? Coefficient back. Coefficient back. So this is the guy. So this is an object in the non-G cusp. So now let's talk about so let's
Is there any explicit formula for EL?
say again.
Should there be any explicit formula for EL?
There will be this before a prayer, just like saying. Smudged everything. So, got confused with my notes. What I should have been proving is this. So, I should have started with this diagram, and I should have shown the opposite of this diagram is itself. So, what I'm trying to identify is the following. I take square F back E L, and I want to show that its opposite is itself. And what we just identified is that this right hand side produces the object, which is EL of planetary bound. All right, and if you think of what that is, so what are we doing here? So we have D mod 1G, we restrict to this D mod U.
Yeah, I don't agree.
Yeah.
What's that? What are you doing right now?
We got confused. So I'm proving this isomorphism.
Yeah.
So that's what I have to show.
No, there, the triangle on the left is like left adjoint off. Or you extend.
Maybe I should take 3 minutes and redo what I'm doing because it's very confusing. So I'm proving this. So my point of departure is the left adjoint counter, and I want to show that it's actually what it's opposite. So I'm taking this triangle.
This triangle you can have L up.
This is L. So what I should have is this. I should have the same triangle as the left. This is what I'm supposed to do. It's not and so
That's this thousand. It's the
And then we can explain.
It's again,
So I can use 5 minutes to explain this formal thing, and then we can do cancel. So do it okay?
So Lynn will do it because I got confused. So let me tell you that main point of the proof and for which everything follows. So here's the main thing. So what I was trying to. Okay. So we have this object Poincare back. And on the one hand, we're taking it, we're applying EL to obtain object in the classical category. On the other hand, you can do the following. You can take this object Poincare back. So I want to say take its Verdier dual. I really can't quite because I'm not quasi-compact.
but you're allowed to take the gradient. It's a constructible sheet.
Yeah, sure. Take Verdier dual. I want it to be more pedantic. And take EL to it. So the crux of the proof is this: these two guys are the same. And it's a non-trivial assertion because if I take the Verdier dual Poincare back, I don't get a total Poincare back. What I get is Poincare star back. So who is this guy? So remember, we have this diagram, this bond and omega going to bond G. It's called smorphism P, and there's a smorphism called evaluations of A1. So Poincare back was pulled back the exponential and pushed forward with this shriek. And if you Verdier dualize, you pull back the exponential and pull back with the star. This is Poincare star. This is really different object because this morphism is not compact. So, and what we are saying is that EL Poincare shriek is the same as EL of Poincare stars. So EL was the left adjoint of the embedding of the classical category to the whole thing. So what this assertion is saying, let's just say that these objects, although they're different, I mean, there's a morphism from one to another because it's a shriek pullback versus star pullback, that the cone of this morphism is purely Eisenstein. And that's what we're saying, that kind of this failure of this morphism is compact, but being compact, when you evaluate the shriek direct image versus star direct image on this exponential sheaf, they're different, but the difference is Eisenstein. And that's what makes it work.
You have to be careful. If you so does not have lower shriek to lower star or
It's a representable morphism.
shoot sorry.
So modulo me being confused about this diagram, this is what's happening. And Lynn, you'll fix it, right?
Yeah.
Okay, good. Let's have a Q&A. So again, I'm done with this proof. Again, modulo, budget with diagrams. Yes.